Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 7.4, arc length and surface of a revolution. Please note that we are skipping 7.3. So let's get right into it today. See what we have here. All right, so our learning goals for today, we're going to find arc length of a smooth curve, and then we are going to find the area of a surface of revolution. So before we get started and get into the nitty gritties of it, and this hopefully will be a fairly short one, I want to have a brief intuition of what finding arc length kind of is. So we have this curved shape, and we don't necessarily have a definition for how to find a curve, especially if it's not like a circle or something that we've seen before. But let's say we want to find the length of the curve from some point here A to some point here B. And so if we follow that up, there's a point there, and you're going to see that this is kind of similar to something we've done in the past. If I say, all right, I'm going to divide this into a bunch of even divisions, and we will call all of those of length delta x, then from here to here, if I take and I find a line, and oh, that's not going to be very nice. Let's make it smaller. If I take a red line and I connect the dots there, and then if I do that again from here to here, and then I do it from here to here, and then if I do it from here to here, and I do it from here to here, and so forth and so on, and I'm trying to show that there is some error, and if I line up all of these individual different line segments, and I find the distance between all of those line segments, and I add those different ones up, well, then very clearly we can see that we're going to have a fairly decent approximation. And that approximation gets better the smaller we make delta x. So the smaller we make delta x, if we let delta x get infinitely small and we have infinitely many line segments, we get and then we add those all up, we get a fairly good approximation of the length of that curve. And so what do we use if we're trying to add up a bunch of stuff? Obviously, that's an integral. Integral as a accumulator. So first, a definition of a rectifiable curve is a curve that has finite arc length. And the definition of arc length is going to be our equation. So if we have some function y equals f of x, which represents a smooth curve over the interval a to b, which means smooth curve means no breaks, no sharp corners. Then the arc length of f between a and b is going to be S equals, and I don't like using S because they look like my 5s, but that's what the book uses, so we're going to have to use it from A to B, and then the square root of 1 plus the first derivative of x squared. And so it's not exactly like the distance formula, but you kind of see that distance formula embedded in here. This is your change in y's, and then the 1 is the x, but we're letting it shrink, that distance shrink to 0. So it's not exactly the distance formula, but it's pretty close. It's close enough for us to discuss it. And then a surface area of revolution is kind of like the volume of revolution, but what we're doing is we're going to find the distance of this curve here, the length of this curve, and we're going to revolve it. And then what we'll do is we'll come up with a surface area. And so again, you can see a lot of that in there. Remember, circumference is 2 pi r. And so what we're trying to find here is a bunch of circumferences, and then we use the integral to accumulate all of those circumferences and add them up, and that finds the area of this surface of revolution. And I took this picture from somewhere else, and there's the credit. And so this r of x is going to be the absolute value of x of f of x, and then this is the first derivative of that thing. It's a pretty straightforward equation. You might want to pause, and I went through that pretty fast. You might want to pause somewhere and get this equation written down, and then pause again and get this equation down. Now, I only have one example of each. So my first one is example number It's not example number 4. It's example number, it's not example number 6. It's example number 4. Let's do it right there, Macaulay. From page 484. So now I feel like I might be dyslexic and I might have switched to maybe it's 486 or something like that. But I'm doing number 4. So they want me to find the length of the curve. And that curve is f of x is equal to, let's see here, they have x to the third over 6, and then plus 1 over 2x, defined from 1 to 2. All right, so we want to find that length right there. Well, first thing I want to do is I want to rewrite this function. So I'm going to rewrite f of x, not f prime yet. You're not quite there yet, Macaulay. Getting ahead of myself. F of x as 1/6 x to the third, and then plus 1/2 x to the negative 1. And the reason I want to do that is because this definition of arc length, this function here is the first derivative, so I want to take first derivative, and this rewrite makes finding that first derivative fairly easy. F prime of x is going to equal to, well, I multiply, so I'll get a half, because it'll be 3 times a 6, the 3's cancel, I get a half, x squared, and then I multiply that, so I got negative 1/2 x now to the negative 2. All right, so there's my first derivative. I'm going to bring this equation for arc length, and it is s equals a to b. In this case, it's 1 to 2, the square root of 1 plus that first derivative squared. So let's write that out. So our arc length s is going to be the integral. Here is our interval, so from 1 to 2, and then it's going to be the square root of 1 plus this first derivative, so I'm just going to put it in there, 1 over 2x squared minus 1/2 x to the negative 2, and I can type that in my calculator just as it is with a dx, and don't forget your squared there. Right there's a square, so the first derivative squared. We have all that we need, and since this is a definite integral, if you look on CalcChat, you'll see that they actually do this integral, but I'm not gonna spend a lot of time doing it, especially since it's got I got a square, and oh, that'd be a mess to simplify. So I just stuck this in my calculator and I came up with 1.417. That is my arc length. From 1 to 2, it's not very long. That seems reasonable. And then I have a surface of revolution equation or problem. And so they give us in number 38, they want to find the area of a surface. Oops, spell it right there, Macaulay. S-U-R-F-A-C-E of revolution. And the equation that they give us is y equals 2x to the half, and they want it on the interval from 4 to 9. Okay, so just real quick, I don't like red for my axes. So there's my axis. And so if I plug in 4, square root of 4 is 2, times 2 would be 4. So there's the first one. And then 9, square root of 9 is 3. 3 times 2 is 6. So I have a curve like this. And so all I'm doing is revolving this around here. And I am finding the area of the surface area of that. I'm not finding the volume, I'm finding the surface area. All right, so I go back and I look at this equation. I got S, and this S equals 2 pi from A to B of R times the square root of 1 plus that f prime of x squared dx. All right, so the first thing I need is okay, this is going to be my f of x. And you know what? Let's rewrite this one more time, because it's going to be my r of x is equal to my absolute value of f of x, which in this case is 2x to the half. And then f prime of x, half times 2 is 1. I get x to the negative 1/2 power. That is my f prime of x. And so now it's just, again, it's just a matter of me putting it in over the interval from 4 to 9. So again, the equation S, this surface of revolution, 2 pi, and again, it's 2 pi r. And so it goes from 4 to 9. My radius equation is going to be this 2x to the half. And then it's times the square root of 1 plus this x to the negative 1/2 squared dx. So it's just me plugging the values that I have into this equation. Pretty straightforward. And again, the book actually does this integral. I wouldn't touch it. I would just grab my graphing calculator, since our graphing calculators do a good job at doing these definite integrals. Be real careful with the half powers and the negative half powers. And I typed it in and it comes out 171.258 units squared. And that is it. Okay, folks, that's a pretty short one. You'll be happy. Only 11 minutes. And the super Star Wars fun fact of the day is the story of Darth Maul. Spoilers. So if you haven't watched all of Star Wars Rebels, you'll get a spoiler here. So we meet Darth Maul here in Episode 1, The Phantom Menace. He is the first Sith that we see in the movie, and he gets chopped in half by Obi-Wan Kenobi at the end of the movie and falls down a garbage chute. But his hate is so powerful. It says powerful hate that he, from the trash, saves himself and creates a pair of robot legs with little claw hooves on there. And he goes on a rampage. And then at the end of season 3 of Rebels, he meets Obi-Wan once again. And Obi-Wan puts him down for the last time. And that is the end of Darth Maul. Well, that's all I got for today, folks. Real short one. Have a great day, and I will see you in class. Goodbye.